All right, starting the recording, officially welcoming everybody. Happy Thursday. Happy last day before spring break. All I want is a couple days off. Huey Lewis in the News said it best. I'd also like to wish my Huey a happy birthday. So this is him this morning. This is a Cookie Monster donut, by the way. It has googly eyes and chocolate all over the bottom of it from Hertz Donuts in Coralville. So one of his favorites. So we celebrated for him already last weekend. We had 9 little boys over to my house to all play Nintendo together. So it was very quiet and calm, as you might imagine. There was definitely no yelling, jumping, or throwing each other around.
Or fist fights over the
There were no fist fights. I did control that. We had the parents sort of on both levels trying to keep everyone alive at the same time. So we will celebrate with him tonight with Steak and Shake, his preferred dining experience.
Sounds about right.
Yeah, a cheeseburger with mayonnaise only, absolutely no other condiments of any kind. That's his dad's influence. His dad, mayonnaise is like the #1 go-to for everything, and not Miracle Whip, damn it, absolutely not. Those are not synonyms. And I didn't know they weren't until, I discovered this portion of the population who believed very vehemently that mayonnaise and Miracle Whip are not synonyms. But mayonnaise on the hamburger, cheeseburger, and a birthday cake milkshake. So, yay dinner. And yay break for the rest of us here. So just to remind us what we still have ahead of time, you'll have a formative assessment due the Monday after break. That is available, and you should be able to answer everything by the end of today at the latest. Homework 3 due after that on your own data. Let us know if you need help, okay? If things aren't working or you're not sure what to do, we are happy to weigh in and give you tips, strategies, and so forth. Just a reminder, it needs to be 3/4 complete. Doesn't need to be perfect. If you give me something to work with, I can give you plenty of feedback, and you'll have an opportunity to revise that as well. Then we have, so what's left to talk about, our next unit after this one is IRT models for what is called polytomous data, or what the rest of the world calls categorical, ordinal and nominal models. That's going to be where most of you are at in terms of your individual data analyses. Then we step into the world of invariance, so asking whether the scales, items work the same way across time, groups of people, that kind of thing. Chris, do you want to put in a plug for your study, since we're on the topic?
Oh, absolutely.
Yeah.
So in a few weeks, you're going to get an email from your lovely instructor who I signed up to be a part of my study on finding, or more accurately, finding bias in student-led teacher evaluations. I would love if you could read that email and be like, oh my gosh, Lisa did such a good job formatting this email that Chris sent her to send out to all of you, that you just are so inspired to fill it out. Thank you.
That's not where I thought you were going to go with that.
Oh, okay.
No, I meant I did such a good job formatting the email,
Oh, yeah, that's
Yes.
Yeah.
Yeah, so there is a research study that this class is participating in. After spring break, you're going to get a chance to fill out a regular course evaluation, but not for the end of the semester, for the purposes of research, which is collected mid-semester. And notably, they will be asking demographic information about you and me. That way we can actually look at potential bias and invariance across different types of classes, different types of instructors, because a lot of the research on this topic has made generalizations without really having the data to back it up, right? So to be able to pull apart characteristics of the class, the instructor, and the students, that's the focus of the study. So being a good steward of research, I signed up. So we'll get a chance to do that after break. I believe it's scheduled for the week right after. So, but yeah, so along those lines, then invariance is looking at whether item properties are the same across samples. And if you do it in the world of CFA, then it's called measurement invariance or factorial invariance. If you do it in the world of IRT or IFA, it's called differential item functioning. So I'll show you how to do all of those things. That will take a couple weeks. Then Unit 8 is higher order and method factor models. So looking at complex factor structures, such as dealing with wording effects or other kinds of accidental sources of covariance that you don't want to have, but you need to address nevertheless. And then wrapping up finally with SEM, the name of the course. So you might be asking yourself, why is she only talking about SEM in the last week? There's 2 reasons. Number one, this should be a full year course, not at one semester. And I'm trying to shove in everything that I possibly can into one semester as a result. But number two, once you get to this point, honestly, it's easy. Building the measurement models and evaluating their fit is the hard part. SEM then is fitting multiple measurement models at the same time and having either slopes or correlations connecting your latent factors. At that point, the structural model is just regression, and it's latent variable regression, but it's just regression. So honestly, like, that is much easier to fit, much more difficult to screw up. So it doesn't take as much time. But then I have more stuff about, like, if you can't do a full SEM, what are your alternatives? Such as parceling, such as using factor scores, plausible values, and that kind of stuff. So that's where we'll end up. So any questions about the class, where we're headed, what we're doing? No? Rumors are good? Zoomers, we good? Doorbell has stopped ringing, so I think we're all good. Thumbs are good? All right, cool. Then I'll do that and go back to this. So what did we start talking about last time? IFA. What's IFA stand for?
Item factor analysis.
Item factor analysis. Give me a synonym for IFA. Or a phrase that is synonymous with that. There's a couple I can think of.
Confirmatory factor analysis with ordinal or nominal?
Yeah, people will call it CFA with categorical outcomes or CFA with ordinal outcomes. When they say it that way, they mean item factor analysis. So they're expecting versions of the model that contain factor loadings and contain either an intercept or a threshold. We'll review those in just a minute. In contrast, IRT is the version of the model that includes A, discriminations, and B, difficulties. And we started talking about how to get back and forth across the two here. So there's two different ways that IFA models differ from CFA models, in their link and in their distribution. Crossover to the other class. So tell me more about that. What's a link function? You can give me an example of one rather than a definition. Logit's a link function. Give me another one. Probit. Synonym for probit? Ogive. How about the natural log? That's a link function. Cumulative log, or complementary log. Cumulative is coming next week. Link functions, what do they do? Why do we need them to predict binary responses, for instance?
Transform the predicted outcome so that it stays in boundaries.
Yes, link functions transform the conditional mean of the outcome, so what the model is predicting, to remain within the boundaries of the outcome itself. So for 0 and 1 outcomes, what we're trying to do is predict the probability of a 0 or a 1. So a logit link or a probit link, those ensure that the predicted probabilities stay between 0 and 1 as they're supposed to. That creates a bendy line in terms of how the trait relates to the item response in probability scale. The same exact technology is going to be used in ordinal and nominal too. So logits and probits are where it's at. What's the difference between logit and probit? I'll take words or a number. 1.7, and if you're Rod McDonald, it's 1.701, specifically. Apparently that was a point that he had to make in his classes, Jonathan says. So yes, 1.7. Probit times 1.7 puts you onto a logit scale. So there are two different ways of doing the same thing, predicting a conditional mean that truly is continuous and unbounded, but then when you back translate or inverse link back to probability, it stays within the bounds. So that's one way that these models differ. Tell me about distributions. What kind of distribution does binary outcomes need? Each outcome, I should say. Starts with a B. I heard it. Bernoulli, yeah. So rather than saying our item responses have a normal distribution, we're saying that they have a Bernoulli distribution for binary. And when we get to ordinal and nominal, we'll say that they have multinomial, which is Bernoulli with more than 2 categories. or binomial with one trial, take your pick. So we're swapping out those two things, but the middle of it, what's known as the linear predictor and generalized models more broadly, is the same. We're still having some kind of location parameter, some kind of discrimination parameter that multiplies theta. And what are some synonyms for theta? Factor something. Yeah, latent factor. True score. What's it called in the IRT class? What is it? Ability. Yes, that makes sense if you're talking about some kind of cognitive ability as the trait. Latent variable, latent factor, latent construct, ability, true score, theta, F. Squiggle 1 in your textbook on CFA models. Did I forget any? Those of you from the multi-level classes, what else could I add to this list? Looking at the TAs, looking at you, looking at you, looking at you. Looking at everybody, actually, I think most of you, and the Zoomers. If I want to make a connection between IRT and IFA models or CFA models into multi-level, what's another word I can use to describe a latent trait? Could be. Starts with an R. Random. Theta is a random intercept, folks. You can fit a Roche model as a multi-level model. If you constrain all the loadings equal to 1, that's a random intercept. Random effects are latent variables. So there's a lot of crossover here. You can think of these models, factor analysis models, as items nested in people because we have controlled for differences in item difficulty as the crossed dimension that you would otherwise have if you let it be random instead of fixed. So just trying to make connections. It's difficult when the classes are taught sort of on one silo topic at a time, but it's good to understand how these things are related and how that leads you to be able to do different kinds of things. Okay, questions so far? Getting our heads back in this? Okay, so we're doing factor analysis, but we're adding a logit or probit link function to make sure that our binary outcome probabilities stay within the bounds. We're switching out the distribution we say the item responses follow to something that is more like what they could follow. Binary data are not continuous. They can never be normally distributed. So then we talked about how to get back and forth across these models. Should we go back over that? I think yes. So item factor analysis as it is written looks a whole lot like confirmatory factor analysis. There's only two differences. Number one, E is gone. So there's no E in this equation right here for binary item factor analysis, and there's no E at the end of the binary regression equations either, for the same reason. Do we remember why?
Because the variance isn't independent, like it's built, it's not an independent thing. It's always the same and it just like adjusts, right?
Yes, the variance is not an independent thing, meaning it's not a separately estimated parameter in distributions for categorical data. It's dependent on the mean. So if I have a predicted probability of 0.5 for my item response, the variance around that is 0.5 times 0.5. So then 2.25. And as that mean goes closer to 0 or 1, the variance around it shrinks. Down to if your mean is 1, there's no variance around it. Everybody has a 1. Likewise, if your mean is 0. So the variability around the predicted outcomes is non-constant and a function of the mean. So we don't have a separate residual variance in these models. And if we talk about the residual variance in terms of the underlying logit scale, do you remember the number that it is? 3.29. Yeah. Pi squared over 3 to be specific. The underlying variance of the probit scale, it's 1. Now why this matters is you're going to see those numbers show up in formulas by which to create standardized slopes in these models because you have to know what the total variance is. The total variance is 3.29 if you're in logits or 1.0 if you're in probits based on how you scale the model. The IRT version of the model looks like this down here. So it looks very different. So in contrast to CFA and IFA mapping onto each other, loading to loading, F to F. Intercept is replaced with this thing, threshold, as it's called, with a minus sign in front, because -1 times your intercept is your threshold, and vice versa. So if we distribute the A as the discrimination parameter in a 2-parameter IRT model, and we rearrange it so that it looks like the same order as factor analysis, we end up with this. So the loading and factor analysis is directly related to the A, and it will be the same number if theta's variance is 1. And the threshold is the same thing as A times B. So you can use these equations to get back and forth if you're using the parameterization that I am. So there's more than one. The one that I'm doing maps onto Probit as an idea. So that means you can decide which version of these parameters you want to have. They are linear combinations of each other. So you can get out your calculator, given one set of model results, and get to the other side. Better yet, you can ask your software to do it, because then you'll not only get the estimate, but you can get a standard error for that combination using a delta method. So I'll show you M+ code to do that, for instance, once we get to ordinal. So you can choose how to talk about your results. If you're used to talking to people who are familiar with IRT models, you might give them A's and B's. If you're used to talking to people who are more familiar with CFA models, you would give them loadings for sure, and then either intercepts or thresholds. The difference is what they refer to, whether it's predicting the probability of a 1 or the probability of a 0. Which one is an intercept? A 1. So threshold is a probability of a 0. So if I told you that my intercept is 2, what's my threshold? -2, because logits are symmetric. So if I know the probability of a 1 is 2, I know that the probability that the logit that corresponds to the probability of a 0 must be -2. And the same thing is true in probits. Probits are symmetric as well. So you only need one or the other. And we looked at this plot. We'll do this one again because I like this one. This is an example of a picture that I kept drawing in Paint over and over again, and then I thought, I need to make a slide. So once you find yourself getting Paint out more than once, it's time to make a slide. That's what I've learned about this. So this is the 3 different versions of the model. They are equivalent. Okay, they are rearrangements of each other. The term for that is alternative parameterizations, if you want to sound fancy. So if you get intercepts and slopes, you're getting the first version here. If you get thresholds and slopes, that's the second version, where slope and loading is words I'm using synonyms. And then if you get discrimination A's and difficulty B's, that's the third version here. And they all map onto the same picture. If we look at the example item 1 here, and its parameters are mapped out. So theta is the x-axis here, and I have in parentheses mean 0, variance 1, because we need to know that to interpret like what these values mean. So this is only plus or minus 1 standard deviations of theta in this plot right here. The y-axis is the probability of a 1, which ranges from 0 to 1, and a probability of 0.5 as our reference point for what B means is marked right here. So this particular item has a B value, difficulty, that was estimated as minus 0.376. That, if I draw a line down from that point, here's where it connects, up to, that's where the probability crosses 0.5. What is that in logits or probits? What is a probability of 0.5 in logits or probits? 0. Okay, so hold on to that, because 0 will make this easier to understand. So difficulty tells you what kind of theta that item is most useful for. This item is going to be most useful for somebody who is like 1/3 of a standard deviation below the mean. Somebody who's on the lower side of the distribution. That person has a logit of 0 or a probit of 0 at that point for this item. So I like B's best of the 3 choices here. That's IRT land. A is a slope. And because this line is bendy, this logistic curve, the slope shuts off, turns on, and then shuts off again as you get close to the boundaries. You can't just say the slope. That's not specific enough. Instead, you can say that A is the maximum slope, which occurs at a probability of 0.5, and that's the point where the curve starts to tip over, or the point of inflection. So up to this point, the curve is accelerating. When it hits this point, then it decelerates instead. So A is the point at 0.5 specifically. A is the slope at 0.5 specifically. If I change this plot and I were plotting logits or probits on the y-axis, how would this line change? Yep. I'm asking you to picture in your mind's eye. If I redid this plot and I changed the y-axis from probability to logits or probits, how would this predicted line change? I'll take gestures. Got one gesture, two gestures. Zoomers, you want a gesture? There's three. I don't know how to gesture in the chat menu, but maybe there's an icon for that. You can find one. And a bunch of abstainers.
It should be like a straight line, right?
Should be a straight line, yeah. So when you write it this way, right, this slope is straight. This is a linear slope predicting the logit. It becomes a nonlinear slope when you predict probability. So as in my IRT class, the model is linear in the logit was a phrase that I got used to hearing, and I had no idea what that meant. Now I understand. The slope is linear if you're predicting the logit of the outcome. The slope is linear if you're predicting the probit of the outcome. When you back translate those predictions into probabilities, then the slope must become nonlinear to shut off as it approaches 1 and shut off as it approaches 0. So A being the slope at the maximum point here, the maximum slope at the point of inflection, is in the probability metric. It is a linear slope in logits and probits. Okay, with me so far? So then if we follow the curve up to another reference point, which is the IFA parameterization or the CFA parameterization, instead of B's, we have either intercepts or thresholds. So next stop is intercept. So the intercept for this model was estimated as 1.629. That is the same as an intercept in any model, in any class, in any world. What's an intercept? Not a trick. What's an intercept? Like when you learned it in like the constant in 8th grade algebra, or when you took your first regression class. What's an intercept? Yeah, the predicted outcome when all your predictors are 0. So if we engineer that into this, predicted outcome means specifically predicting the probability of a 1, because that's the conditional mean that that's being predicted. When the predictors are 0, what's my predictor in the IRT model? Also not a trick. Theta, the trait. The factor, the trait, the construct, whatever you want to call it. That's my predictor. So for a predictor value of 0, an intercept tells you the predicted logit that corresponds to a probability of a 1, or the predicted probit. So that turns out to be a probability of 0.836, which is where the red line crosses the y-axis here. So intercepts tell you what to expect from a given item for an average person. They are anchored relative to a theta of 0. So for an average person, your probability of this item is this item is this item is this. To me, that is less useful than B, which tells you how much theta you need for a logit or probit of 0. So intercepts tell you y when x is 0. B's tell you x when y is 0. Nodding. You like that? Yeah. This stuff is hard, but if you boil it down to just something's got to be 0, one of them is 0, then that's the difference. B tells you what x is when y is 0 in logits, and intercepts tell you what y is when x is 0. What y is when x is 0 to me is less helpful. Because it takes some extrapolation to be like, well, what if x were 1? What if x were 2? Now, this would be lovely if this is where we ended up. However, these two things are going in opposite direction. A very high b value would be like 3, meaning you need a trait level that's 3 standard deviations above the mean to have a 50-50 shot at getting this item right. That's a hard item, very difficult. But if you had an intercept of 3, that means you are almost guaranteed to get it right at a theta of 0. That's an easy item. So intercepts, because they're added, are easiness parameters, the same as they were in CFA. Higher values mean the item is less difficult, whereas B's, because of the minus sign here, are difficulty parameters. And I believe that is the motivation why you will get these stupid thresholds instead, is to make them go the same way. So the minus sign here is our clue for how we can interpret the threshold. So if my intercept tells me the logit of the probability of a 1, by multiplying by -1, I get the logit of the probability of a 0, because logits and probits are symmetric. So then that gets me to what the actual intercept parameter would be. 1.6 turns into -1.6. And that corresponds to, is that the complement, like the opposite? Is that the right word? Math people, anyone? I say opposite, but I'm pretty sure that's not the right word. But 1 minus 0.836 is 0.164. That's what I'm saying. There's a word for it, right? Complement? I got it right? Yay! Yay me. Okay. So, now your quest, when you're trying to fit these models in practice, is to figure out what you got. Much easier said than done. So there's 2 ways to do that. Number 1 is to take a data set where you know what the right answers are and see what your software spits out, and then try to rearrange what you get until it looks like something that you know. Number 2 is to make up data. And this is something that I do when I'm not sure what software is doing or I'm not sure how models work. I make up data where I know the right answer, and then I see what I get back when I fit the models to my made-up data. And I make up a sample of like 100,000 people, so there's no sampling variability at all. Like it's going to get locked into the population values. But you don't have to do that because you have me. They pay me so that you don't have to figure this stuff out by hand. But I've only figured it out in a few different packages, in Stata, in ProcIRT, in M+, and in Lavon. I believe MERT defaults to slope intercept. Is that true? That sound right? What does Stan do? Anything? Does it default to anything, or is it just whatever you write? Whatever you write? Yeah, okay. That's one that I will not add to my list. If you'd like to learn how to use Stan and JAGS, as I mentioned in my email yesterday, Bayesian psychometric models is coming back this fall by not me, by Jonathan, and he will teach you how to do psychometric type analyses, CFA, IFA, and so forth in Bayesian estimation instead, using that. So, would recommend that for those of you who want to know more about this topic. All right, so then, all the words of what I just said. Loading is the same thing as A. If your factor variance is 1, it's rescaled by the factor variance otherwise. Intercept tells you the value of y for probability of 1 when theta is 0. Threshold tells you the corresponding probability of 0 when theta is 0. Difficulty tells you the amount of theta needed to get to a logit or probit of 0 instead. Okay. How are we doing with this idea? Now, the reason that you haven't seen an example yet, by the way, normally I like to mix in the example and we sort of sprinkle it through the slides, is because literally you have to have all of this to understand M+. Because what M+ is going to give you is this, the middle one, thresholds and loadings. For binary outcomes, it also spits out the corresponding A's and B's. It does not do that for polytomous data, though, so then you have to make those yourself. And when you estimate the model with full information maximum likelihood, you get no index of how it fits. So I want to tell you why that is. But if you switch to a different kind of estimation, then you do get indices of fit, and I want to tell you why that is. So I kind of have to tell you everything first before even the first model will make sense, unfortunately. That's how it is. But I got a few pictures and stuff here. All right. Beyond those discrepancies, different versions of the same solution, you can also get standardized parameters, and they mean the same kinds of things as they do in CFA to a point. So the standardized solution is trying to make it so that either the error variance is 1 or the total variance is 1. In the way that I'm going to teach you, it's going to be the latter. So the total variance that is implied by the model to be used in the standardized solution is the same as it started off in CFA, the loading for that item squared times the variance of the factor, or theta, and then plus 3.29 or 1. What dictates which it will be? Logit or probit. Logits are 3.29, probits are 1. So once you have that, then you can create standardized thresholds using the unstandardized loading and the standard deviation of the total for the outcome. You can create standardized loadings using the same type of idea here. However, same caveat applies. This standardized loading in logits is a single slope, right? But when you back translate it into probability, it's a bendy slope. So before in CFA, we could look at our standardized loadings and be like, that's a good item, that's less good, right? I can still do that, but I have to remember good where. This is a good item at this difficulty level. This is a good item at that difficulty level. That has to stay part of the story. And there are papers, I have seen them, in which people use standardized parameters to compute omega as a measure of reliability. These models do not do that. It doesn't make sense. Because the slopes shut off as you move away from the difficulty value, the extent to which that item contributes reliability, contributes information, is non-constant across theta. So I don't think it makes any sense to come up with one number that describes reliability. It only makes sense if you're saying it's reliability on the logit scale, but nobody wants to know that. Like, nobody thinks in logits. Logits are just a trick to make sure that we can have a model that makes sense. All right. How are we doing? Now, what other kinds of outcomes are there in the world? We have normal, binary, ordinal, and nominal that we've talked about. Can you think of any other kind of outcome variable that you might care about in life? I'm going to call on your TAs. Cass? Like, what were we talking about like an hour ago? Counts. So we're working on a project that we're looking at the number of disciplinary actions for a child and attempting to try and create a latent trait for that. That seems like a thing we could do, right? But it's like, how many times did you get in trouble for punching your friends? How many times did you steal someone's lunch money? How many times did you get expelled for smoking pot? Like, these are the things. So we could cut that up into has happened or not has happened. Not has happened, is that even words? Has not happened? Has not happened? Yeah, I need a break. That's where we're at here. I has needing a break. That's very kind of you to blame it on a language issue, but no, I'm just fried. I've already had my requisite caffeine for the day, so there's no more. I'm back to 7-Up. But yeah, we could have counts, right? So let's see, what time is it? 1 o'clock? In an hour from now, we're going to start talking about counts in the other class. And those of you who've been through generalized, right, we can predict counts. Could I put a count model under a factor model? Could I say that theta predicts your count of disruptive behaviors? Sure it could. I just need to swap out my link and my distribution. So the link that we use for counts is almost always just the natural log, because counts have a lower bound of 0. They go up to positive infinity, and the natural log ensures that predicted counts stay above 0. Distributions for that, our friend Poisson, negative binomial, potentially 0 inflated versions of either of those, and a few more that I don't talk about in class, but that I know exist. What other kinds of outcomes? Let's see, proportions. Could we have a proportion? Like the percent of the time you were absent from school, something like that. Okay, so proportions are bounded between 0 and 1. That's our friend logit again. That two boundaries means logits or probits, but proportions are continuous in the middle. So then that's some kind of binomial or beta binomial that goes with that usually. What about things like response time? Could I have a speeded measure of cognition? How fast you can answer these questions? Sure I could. What's response time look like? Bounded at 0, up to positive infinity, continuous. So that might be a log link and maybe a gamma distribution or log normal. What about response time and accuracy? So there's a project that I helped with that turned into a student's master's thesis at Nebraska, and I like this one because it's a good example of how not knowing generalized can cause you to do dumb things with data. So there was this task involving adolescence and decision making. And teenager brains mature at different rates, and there's sections that do not fully mature until your 20s, and that's why teenagers do stupid shit. So there was a task designed to elicit them doing stupid shit, but in a safe way. So they were in this task where they were driving in a car, and they were told they had to get to a party, and they were going to be late. But then they had to go through stoplights and yield signs and things, and every time they hit an intersection, they had to decide whether to floor it and go through the yellow or to stop and hit the red. And so one of the measures of this task is their latency to make that decision, whether they're going to floor it or stop. And if they stopped, then they didn't have if they didn't stop, they didn't have a latency. That's how it went. Like if they stopped, we have how long it took them to stop. But if they decided to floor it, they didn't have that. So what they had done in analyzing this task was just throw out the trials where they stopped. Or they didn't stop, have it backwards, didn't stop. Yeah, in that face, like what? Like isn't that trait relevant variance when you decide to floor it through the intersection? Isn't that supposed to be related to this impulsivity trait or whatever this task is measuring? Yeah. So I helped him fit a model in which it was essentially what's known as a hurdle, where you have, did they stop, yes or no, as a binary indicator of a trait, and then if they didn't stop, how long did it take them to make that decision? Or damn it, I'm saying it backward every single time. If they stopped, how long it took them to make that decision? So two different types of indicators out of the task, and it turned out that only one of the factors was related to the other outcomes they were interested in and not the other. So if you understand how you can kind of swap out links and distributions underneath these things, then you can analyze any kind of data using structural equation models. The only catch will be finding software that has all the combinations that you want. And that's where people would, to quote my husband, say roll your own and start programming models in Stan or what I know of as like NL mixed in SAS or other packages where you can write whatever algorithm you want to fit the model. So this is just a placeholder for that idea, right? We don't have time to cover all the possibilities, but you can fit a factor model to any kind of outcome that you can match to a link function and a distribution. There's my sales pitch for generalized structural equation modeling. So for this unit though, a lot is made of whether CFA responses, whether they're normal enough to be able to fit a CFA. That's really not as important, I think, as this idea of boundaries. Like, does your model predict item responses that cannot happen at expected values of theta? If it does, it's not a good model. All right. So, summarizing intermediately then, IRT and IFA are factor models. The IRT version has parameters of difficulty and discrimination. The IFA version has a factor loading and either an intercept or a threshold. So the form of the relationship between an item response and the latent trait it's supposed to measure depends at a minimum on location. So we will either have a B or a threshold given in the same metric here for everything, and potentially items would share a slope. If we're willing to let items have different slopes, then we can add some kind of slope that differs across items, discrimination or factor loading, and then we're no longer assuming equal discrimination. So Roche model, tau equivalence, same idea. Can you constrain the loadings to be equal and not hurt fit? You can also add upper and lower asymptotes, and God knows how many other types of IRT parameters that are out there. However, the consequence of this idea of a nonlinear relationship between the trait and the probability of a 1 has implications for reliability. It's now trait specific. It depends on how many items you have and how good they are at those locations. That's the big picture. But unfortunately, before we can look at answers, we got to talk a little bit about estimation. This is the big picture view, okay? Big picture view. To be honest, this is as much as I know. This is not my strong suit. I don't write algorithms for a living. That's not my jam. I don't have training in mathematical statistics. That wasn't my jam either. Going back, I would have made different choices, but I can't do that now. So I can give you the high points. There's readings on your reading list, and if you're interested in knowing more, I can direct you to sources that are more technical, that get into the nitty-gritty of this. What I need you to understand is why, when you fit these models with full information, maximum likelihood, it takes forever and there's no fit. That's what I need you to understand, okay? All right, so what all do we have to estimate? Let's say that we have an example with 7 items, because that's what example 5 is going to be, and we're fitting a 2-parameter model, so logits for this example is fine. If we then have each item with a separate discrimination and each item with a separate difficulty, that's 14 parameters. So that's 14 things that the model has to figure out what the most likely version is of and spit out as results. So these items are being treated as fixed effects. And by that, I mean we get a separate A per item. We get a separate B per item. They do not have a distribution. That means that items and persons are no longer cross dimensions, and items sort of fold underneath. So we can't make any inference about an item that's not in our sample. Like, each one is item specific. The thetas, however, these are being treated as random effects. So F is the same thing as U in multi-level notation. They have a distribution. We don't actually need to know what theta is for each person to make this work, even though theta is in the equation. But we do have to do something about the fact that we don't know it. So we're working with theta's means, variances, and covariances across theta, but not the theta estimates themselves. So there's historically 3 different kinds of estimation methods that have been used for these models under the category of full information. So what that phrase means is uses all the original data, full information. You'll hear this phrase in terms of what happens to missing data. Missing data were addressed using full information maximum likelihood under an assumption of missing at random, or FIML. You heard that phrase before? That's what it means. FIML means I used all the data, not a summary thereof. So it makes a difference when you have missing data, whether you're using all the original data or a summary, because the summary doesn't know what it's missing. So historically, there were older methods used, such as conditional maximum likelihood. This is only appropriate for Roche models, because what they do is replace theta with the sum score, because the sum score is sufficient in Roche models. So that doesn't work if you have anything other than a Roche model. Joint maximum likelihood pretends that the thetas are fixed effects, so it tries to estimate as a model parameter a separate theta for each person. That blows up in a hurry because the more people you have, the more thetas you have to estimate. Whereas normally more people means more precision, it actually makes it worse instead. So we don't do these anymore. The gold standard in terms of maximum likelihood is what's known as marginal maximum likelihood. And you will know that your software is doing this if you see any of the following words in your documentation: numeric integration, numerical integration, quadrature, Gaussian quadrature, adaptive Gaussian quadrature. Any of those words, that's this. So the marginal part means that we have to marginalize across theta to figure out what the item parameters are going to be. And we are using the idea of height still, but swapping out what it is. So we're using independent outcomes because they're supposed to be independent after controlling for theta. So it's not a multivariate distribution that's being maximized, it's a univariate distribution for each. So we're assuming 2 things: that after you control for theta, that items are independent. If they're not, you need to build in stuff to the model to allow them to have extra relationships. And we're also assuming that subjects are independent, no clustering or nesting. So for instance, if you have kids in schools, this one's broken. You would end up needing a school theta and a kid theta, multi-level thetas. If you had longitudinal research, you'd need like a time theta and a person theta. So you need multiple levels of these things. So step 1 is to get starting values for all the item parameters, such as using their classical test theory versions of difficulty and discrimination. We compute the likelihood for each subject given the parameter values. So we know what the probability of a response is given the item parameters on this current iteration. To get the likelihood per subject, we take the product over all the item responses for that person. So the probability of a 1 if that's what you got, or the probability of a 0 if that's what you got. And then to figure out the theta part, we essentially have to try on a whole bunch of potential thetas, figure out what the likelihood is under each, and then average over them in a weighted average, because we don't know what theta is for each person. So that process is called integration. And it's done by Gaussian quadrature, which means cutting up the theta distribution, or the posterior for it more technically, into rectangles. Once we decide if you have the right answers, which means that the height doesn't change across multiple different guesses for your item parameters, there's some standard by which it decides it's done, and if not, pick new ones. And this is where I'm just going to wave my hands, okay? New ones happen through calculus or the EM algorithm, derivatives, stuff like that. But this picture is the big idea. I don't remember who I stole this from, but I stole it from the internet a very long time ago. The idea of integration is trying to find the area under a curve by rectangling the area and then adding up the areas of the rectangles. So this picture would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rectangles. Those are known as points of integration, or quadrature points. How many rectangles you're using. So the idea is that we would essentially try on each of these thetas. What if my theta was -3? Okay, then given these item parameters, here's the probability of a 1, here's the probability of a 0. What if my theta was -2? Now here's my probabilities. So how many points you have differs across software packages in terms of defaults. So for instance, M+ uses 15. Stata, when it does multi-level models with link functions like this, uses 6 as a default. Proc NL Mixed uses 30. Any other ones? This is in the documentation. Some software packages decide how many to use and then go with that for you. So here's an example of the process, of what it would look like. So let's say that we have A of 1 for both items for convenience so the math gets easier, and that item 1 in the data has a mean of 0.73. So 73% of the sample got this item right or said yes to this symptom. That corresponds to a logit of +1, which would correspond to a starting v-value of -1. Likewise, if item 2 had a mean of 0.27, then that would be the opposite, corresponds to a starting value of this. So this is a reasonable place to start. So here's my IRT model. If I use A as 1 and then B are these potential values for the items, we have 3 potential theta values to try on in this. So just 3 for one person. So one person at a time, we're going to go through this. All right, so for item 1, our current guess for what the B value is -1. Well, my best guess right now for my theta is -2. Put that in here, minus a minus, that leads to a plus. So I have a predicted logit of -1 for item 1 if the theta is -2. Well, I know in reality what happened. I know if they got the item right or not. So then I take the model predicted probability that goes with what happened. So in this case, if they got it right, they only had a 0.27 probability of getting it right if their theta is -2. Now that makes sense, right? Because their theta is lower than the difficulty value of this item. The item is more difficult than they are smart. If the theta is -2, but the item is -1. For item 2, if our current guess as to what B is +1, that gives me a logit of -3. And now they're even less likely to have gotten it right if their theta were -2. So I have these 2 predicted probabilities if they got both of these items right. I multiply the 2 together and I get this number. So this represents what I would expect given these item parameters if this person's theta were -2. Okay, with me so far? Now, how likely is a theta of -2 if theta has a mean of 0 and a standard deviation of 1? You can use words, not numbers. How likely is a theta of -2 if my mean is 0 and my standard deviation of theta is 1? Not super, like you're kind of out in the tail there, the lower end. So that's this part. If I have 3 possibilities here, I have to cover the entire range of theta. So essentially, like I'm talking about the lower 10% of the distribution being represented by this -2, that's not very likely. So I downweight this likelihood by multiplying it, and then I get this product right here. Now we go through the same process again, same person, same items. Now what if their theta were 0? Well, now I plug 0 into the IRT model. I get these predicted logits for these 2 items, and now these are my probabilities. So right now it looks like theta of 0 is more likely than a theta of -2. Now how likely is a theta of 0? Like the most likely, right? That's the middle. So we upweight this one. And then the same thing happens with theta of +2. So we essentially have like, what is the probability of what happening under this theta, this theta, this theta? And then we weight those based on how likely those thetas are. And then you sum across this, and then you get one number. So picture this happening like churning along. We would try on 15 thetas per person, or 30 thetas per person. And we come up with this weighted average of that person's contribution to the likelihood without actually knowing which one is right for a given person. So this is the idea of numeric integration. What happens in the first pass is we try to figure out across all the thetas. The adaptive version then essentially re-rectangles the part that's most likely to get a finer grained perspective as to what theta would be for that person. But this is one trait. What if I had a 2-trait model? Could I do that? Sure I could, right? I can have a 2-dimensional IRT model, 2 thetas at the same time. Now how many tries do I need? If I have 15 per dimension, and I have 2 dimensions, and I got to cover all possibilities, 225. What if I have 3 traits? It's like 725, I think. I memorized this once. Yeah, so it gets exponentially higher the more traits you have. And at some point, M+ will tell you, no. You just requested 8 million points of integration. No, stop it. And it just won't do it. So this is an example of when Bayes can fix it. Any type of model that involves link functions and latent variables or random effects is a candidate for Bayesian estimation to make it go when the model collapses using numeric integration. That's where that type of methodology shines, because then you're using more of a brute force search process, not this integration type process. Okay, so big picture. In full information maximum likelihood, the more thetas you have in your model at once, the harder it is to estimate the model parameters, because you have to go across all of these different possibilities for what theta could be for each person at each iteration of each item parameter guess. It's a lot. Now, what if I want to know what theta is? You know what? You don't need to know. This could be the last step. Using whichever is most likely, it figures out what the optimal item parameters are that make everyone's data the tallest under this try-on system, and it's done. You don't actually need thetas. That's the whole point of SEM. If you want to know how theta relates to stuff, then you put the stuff in the model with your measurement model, and you have theta as a circle directly predict something else with a slope, or directly correlate with something else with a 2-headed arrow. That's the beauty of SEM. That is why we're using M+, because R won't do that. Lavaan does not have full information maximum likelihood for these models. MERT doesn't have SEM in it. It only has measurement models. So the only way that I know how to do this is M+. There are other ways, but they're more painful. SEM, The package Instata will do this as well, and GSEM has extensions for link functions and whatnot. But if you wanted to have thetas, I have a couple slides on that. I'm not sure how much time I want to spend on this, but the idea is that we can use the same sort of search process. Like, what if for like 5 items for this person here, I know the item parameters, I know what happened, so I can figure out like what is the probability of a person having this result if this were their theta, if that were their theta, if that were their theta, if that were their theta, and you can figure out which one is most likely. It uses calculus to simplify this process, so you can figure out like along the dimension of theta, you're looking for the point where the slope of this line that's tangent to the curve, the first derivative is 0. And if we started over here with our guessing, then we look at how that slope changes, and the point at which it crosses 0 is the right answer. So there's more details about this in the IRT book. I think I assigned a couple chapters about that, and I can give you some other resources. But point being, you can figure out through brute force or calculus what the most likely theta is for each person if you need to have that information. In order to actually do that, though, we have to bring in Bayes. So if you're using straight ML, you can't get a theta for somebody who has all zeros or all ones. You have to borrow the idea of a multivariate normal prior distribution to get some kind of answer for that. So what theta actually represents when you predict it after the fact like this is a middle of a potential distribution for each person, where the width of that distribution is a function of the standard error of theta. The standard error of theta is based on information. So the more information you have at that theta, the more items you have of that level of difficulty and the more discriminating they are, the narrower the ranges of what each person's distribution is for what their theta should be. So any theta that you output as a prediction should have some index of its imprecision along with it for the ride, the standard error. Otherwise, we're pretending it's perfectly reliable, and that's not going to be the case. So the thetas that you get back, you will either get what's known as MIP estimates or EAP estimates. EAP is the preferred version. MIP is what you get from limited information, which we talk about in a little bit. So we will have EAP estimates in CFA models as well as IRT models estimated using maximum likelihood. All right. Now here's why we're not going to get fit. Do you remember model fit in CFA? Like, give me some words that you remember from that unit. What letters do we look at for model fit? CF something. I. CFI is one. Give me another one. What one? TLI. Yep, those two are together. RMSEA. Yep. Acronym soup here. What's another one? Yep, Zoomer's got it. CFI, RMSEA. SR something. SRMR. What about the chi-square test? Likelihood ratio test against the perfect model. And we can see how much worse than perfect we are and how much worse than close we are. And CFI and TLI are how much better we are than the worst thing. So all of those need benchmarks, right? We got to know what is the height of best, what is the height of worst, so we can figure out where we are relative to those things. That's gone. What best is the full contingency table of all possible item response patterns. That's the saturated model. So to figure that out, for instance, if I have 24 binary items, which is what you're going to be analyzing in homework 4, the same gambling data, the number of possible parameters, degrees of freedom, is 2 to the power of 24. Yeah, eyebrows are like, what? Yeah. Right? Because if you think about all the possible combinations of zeros and ones across 24, that's what this is. So it's possible, which is 16,777,216, minus the number of A's, which would be 20, could be 1 if it's a 1 PL, it'd be 24 if it's a 2 PL. Number of B's, which would be 24, minus 1, because then it sums to 1 if you don't know the last one. So we're down to this. So do you remember learning chi-square for the very first time, like back in intro stat? It's observed minus expected squared over expected, and you add it up across all the cells. There was a caveat about when you don't trust chi-square, and you should do like an exact test instead. Remember this? What was the caveat? There was a magic number that I learned. The Zoomers are laughing at me. Do you remember the caveat? He's like, nope, camera off. You can laugh at me in peace, it's fine. 5. That was the rule that I learned, is that each cell had to have a minimum expected count of 5 or it fell apart. And then you needed to do some kind of exact test. All right, so I have 16 million cells here, times 5. Am I ever gonna have a sample that big? Nope. And 24 items is not even that many, like relative to achievement tests. It may have hundreds of items. So yeah, there is no way in hell that I can say whether the saturated model as this ginormous contingency table is adequately reproduced with my model, because I don't have a way to fill out all the possible combinations. And it doesn't stop programs from giving you information about this, but there are 2 different types of chi-squares given, and in the M+ documentation, they suggest that if they don't match, they should not be used. So basically, this is never going to work. There is no universe in which you have enough people to fill out all the response patterns unless you have like 1 million people and 3 items. Then it probably would be okay. So what we're going to get on our output is the HO, log likelihood, AIC and BIC, and that's it. Good luck. So that's dissatisfying. How do I know if it fits? How do I know if my 24 items actually measure one thing? It turns out that it's very difficult. So what happens under full information maximum likelihood? There are IRT programs that provide indices of fit that have nothing to do really with the dimensionality. They have to do with how the items fit and the people fit. And I'm not going to cover these because they all require you to output theta and then do something to it. But if your model doesn't fit in the first place, that estimate of theta is wrong. So it becomes like tautological. So we're not going to do that. In M+, you can ask for a piece of output called Tec10. And what it gives you is the start of the all possible ways contingency table. It will spit out the univariate proportions. So literally, like, you have this many zeros and this many ones in your data. According to your model, you should have this many zeros and this many ones. How close do they match? Usually this is fine. Because each item gets a separate difficulty, it should render this part okay. Then it gives you every pair of items as a 2-way table. 0 and 1 for item 1, 0 and 1 for item 2. What did the data say? What did the model predict? And then how far off? So how many possible pairs are there for 24 items? It'd be 24 times 23 divided by 2. That's a lot. I'll just abbreviate. Over 400. Who wants to scroll through 400 chi-squares to look for how well your model fits? Said no one ever, right? This is annoying. So folks have been working on this, and I will point to some of the newer work in this area to try to find a way to use this idea of, does it fit univariately, marginally of zeros and ones, and then for each pair of items, and to come up with a fit statistics for that. So there's stuff called M2, where this is not squared, it's like lowercase 2, subscript 2, RMSEA2, SRMR2. This means the fit to just the 2-way tables and below, because we can't have the fit to the full table. So there's work trying to find these sorts of, develop these metrics for full information IRT models. That is available within R. There are various packages that do that. It's not currently implemented in M+, but I suspect it will be at some point. So this is painful. Yes, questions?
In a way, could you say this is information parsimony, right? Going univariate first and then applying bivariate?
Yeah, so the question was, would you say this is like information parsimony? I think the way you can think about it is like, if it doesn't replicate how many zeros and how many ones you have, it's way broken, and that's horrible, right? Like, that's terrible. If it doesn't replicate the 2 by 2, it's certainly not gonna get at the 3-way table, the 4-way table, the 5-way table, up to the 24-way table. So, like, most of the misfit, I think, will be caught at this level of precision. There's still potential for more of it, but you would have to have enough sample size to be able to go further. So it's like the 2 in these things means up to the 2-way tables, essentially. In categorical data, there's more to the story than just mean, variance, and covariance. It's the higher order moments show up as part of the distributions. And so that's what the 3-way, 4-way, and 5-way are getting at. So, does that answer the question? Yeah, thank you for the comment. So this sucks, and we're not going to do it. You know what we're going to do instead? We're going to hack it into something that looks like CFA. WLSMV. So, yeah, I don't need to say that. There's words. Limited information estimation. It is called diagonally weighted least squares by people who use non-M+ software. That what WLSMV stands for is weighted least square parameter estimates that use a diagonal weight matrix and a mean and variance adjusted chi-square test. Like, what? Here's what it is. Okay, big picture. We're back to an answer key covariance matrix. We're back to a saturated H1 model. We're back to a null model. We're back. But it's not a Pearson version. It's a different version. In Pearson, the maximum correlation that 2 variables can have is a function of their means. So for instance, if I have a variable that has a mean of 0.5, and I want to know how related it is to a variable that has a mean of 0.9, the highest that Pearson correlation can be is 0.33. So our standard covariance or correlation matrix is not going to work to capture the relationships among these variables. But you know what is? You know what is? You know where I'm going with this? Starts with a T. Yeah, technichoric, that's close enough. Yeah, technical choric, something like that, tetrachoric. So I showed you this slide or a version of it like a month ago, maybe 2 months ago. How long is this damn semester? 3 years ago, I think? That's what it feels like anyway. It feels like a very long time ago. So I have the line of suspended disbelief here. So Pearson correlation, phi or phi correlation, I don't care which, and point biserial are all the same thing. These two have special names for computational shortcuts, but they're all based on means, variances, and covariances, and they're not going to work well for binary or ordinal data. So we're going to use the ones under here instead. Tetrachoric is between binary items. Polychoric is between ordinal items. And the bi or poly serial is continuous with either binary, which is bi, or ordinal, which is poly. And so these are alternative versions of a correlation matrix that in this estimator, it's first going to figure out what the data say that matrix should look like. Then it's going to figure out what the model says that matrix should look like. Stop me if you've heard this before, right? And how well the data matches the model. We're back. We're back to CFI, TLI, RMSEA, SRMR, and all the things, because now we have an answer key again. So practically speaking, whenever I need to look at model fit for these sorts of outcomes, this is what I do. It's much easier. Now, you can't get everything for nothing. The downside of this is that anytime you summarize data into a covariance matrix and then estimate the model using that covariance matrix, you don't know what you're missing. The summary doesn't know what it's summarized over. So what that means in practice is that we're assuming missing completely at random for any missing data, meaning what it sounds like, that the probability of missing this has absolutely nothing to do with anything. And that's usually a really strong assumption. So these methods are ideal when you have complete data or nearly so. They start to fall apart in practice when you don't. Okay, 142, that's enough for today, I think, for this week. So I got the pictures coming up, got some new pictures. But yeah, this is where we're headed, is a new kind of correlation matrix. Yeah, almost done with this. Excellent. Yeah. Then we'll be ready to start an example after we come back from break. That's exciting. We'll have to relearn it all. I know that. Yeah, no, it's fine. Like I plan to re-go over things as needed because nothing is going to sink in the first time. This stuff just doesn't work like that. If this were something where you could read it and 10 seconds later be like, I got it, then you're wasting your money and time in graduate school. So, yeah, we'll re-go over it. All right, 143. Any questions or comments before I let you go? No, we all want to go, don't we? Yes. All right, no class next week, no office hours next week. I will be on email sporadically if you need me. Otherwise, please recharge. Get caught ahead, get caught up, go have fun, sleep, do your laundry, whatever fills your cup, so to speak, right?
Will we also be not on office hours?
That is correct. No, the TAs don't have office hours either. No, it's spring break. Yes, so.
You mean you use this time for a break?
This time I do. We're going to the Great Wolf Lodge
Oh,
in Kansas City, an indoor water park for my son's birthday extravaganza. So pray for me. Pray for me. All right, Zach has a question.
My question's rather specific and individual. But I was wondering, so I also have count data that is zero inflated. And so all we've done is a log transformation. And I was wondering what you thought of that, if that's, yeah. And we're doing a confirmatory factor analysis. So.
Okay. I would say that that is probably, like, if you can't do anything else, I would do that. I think that's a reasonable thing to do. You can fit, and I have examples it's actually, I don't know if it's posted or not, but I know I have an example that has zero inflated data. You can fit that type of distribution in M+, a zero inflated count. And depending on the type of inflation model you want, you can actually have a separate factor for inflation and then another latent factor for the count. So in your context, like, what kind of count is it?
Frequency of engaging in different behaviors. Actually,
Okay.
almost identical to yours. Like how often they smoke weed or something.
Okay, so the example that I have is like that. It's like the number, like there's marijuana, alcohol, speed, like they have like 6 different categories of drugs you can do in the example that I had. And the way, so for those kinds of phenomenon, I like the hurdle models better than zero inflated. And actually, this is coming up in my class, the other class. This is the unit we're starting today, so I'll point you towards those materials. It's on the 670 website. In that case, what the model would do, if you go with a hurdle, is it splits each outcome into 2. There's, do you do any drugs? Yes or no? And so then that's how they handle the extra zeros, is by kind of giving it its own thing. And so then it's like, are you a drug user? That's theta number 1. And then within the people who are ones, how addicted are you is theta number 2. And so I like that because for this type of context, like drug abuse, there's going to be a lot of people who have no problems at all. And then there's going to be levels of severity for the people who do have problems. And this model captures both that qualitative distinction, are you a drug user? And then what is the severity of your drug use if you are?
Huh. Okay. And you said that information about that is on your course website, and it would be called a hurdle?
Let me show you where it is. So the screen share is still on. So in the context of M+, I think I put up links to it because I was pretty sure. Yeah, I don't have a link to it yet, but it's right here on our course. So I have bonus material, example 6C. I have not had time to do that example since 2018. So this is the version of the course I taught at KU. But if you scroll down to that example 6C, measurement models for other not normal outcomes, that example is using M+, and I'll pull it up real quick. Maybe not real quick, as it turns out. So these are the item response distributions for 6 items. It's actually an ordinal scale, but I was pretending it's a count. But like the ones that are like real drugs are heavily zero inflated, whereas we've got cigarettes, beer, and liquor that are a little more county. So this handout walks through the possibilities of a normal CFA model, Poisson and negative binomial, zero inflated versions of those, and then the hurdle versions in 2-part. So then we have examples of how that would look and be interpreted in each of these cases. So if you wanted to try that for like homework 5, I would let you. We could work with that.
Okay, thank you. Thanks. Yeah, I'll definitely take a look at this.
Cool. Thanks for the question.
Thanks.